Yeah. All right, so guys know we're recording this, right? Okay, so recording's going right now. Let's see, on the Spine Tuesday. All right, so stuff to talk about here. In this class, we're gonna do a couple of labs today. I want to keep your guys' minds engaged, but not super overtaxed, because I know most of you guys are going to be taking the SAT tomorrow, right? So we're going to end the class today with some demos. Right. Oh, top scientists. So yeah, that quiz was apparently quite a beast, but you guys did quite well in comparison to other classes. Yeah, so good job there, especially if you see your name there. So there you go there. So someday we'll go over the answers to that, but not quite today. Right. Then SAT tomorrow. So yeah, let me hit some administrative stuff. I got an email from front office, says they've got some big old pile of like books and supplies and lost and found stuff. I did glance through there. I didn't see your guys' names on any of the stuff, but could have missed something. So think there's a textbook or something you might be missing, then making a call for that. Right. Registration. Now, since it's third block, we're not doing any registrations exactly this hour, but just keep your mind on that we're in the middle of registration season right now. So this is uploaded to Google Classroom also. It's been up there a while now. Right. And then I have told you guys where to go. If you are taking the SAT, then there's a page online that tells you which room to go to. If you're not taking the SAT, I do have a handful of you who are, I think, sophomores and seniors. You're not taking it. Is that right? Okay. So don't come to this room if you're not taking the SAT, because we'll be testing in here. Right. Instead, 4223 with Parsons. Right. Okay. So, and I think that just applies to this list. I'm pretty sure. Right. Right. So, who has a question about where they're supposed to be tomorrow? Any question about SAT tomorrow? Right. All right, so let's take a look at the starter question. Right? And this is a different kind of starter question because I haven't actually given you guys enough information to be able to solve this yet. But hopefully by the end of the class today, you'll have the tools that you need to solve this. Right? So you guys remember how yesterday, one of the Kahoot questions, I had this guy hanging exactly from the middle of this beam. Let's say the beam itself was approximately massless, right? But he had a weight of 500 newtons. Right? And remember the tension in each rope was 250, 250 here, 250 here, right? Okay, so hopefully that made sense. Hopefully you got that question right. Okay? You guys do know that the vertical forces have to sum to zero for equilibrium, right? Okay. But then I did ask a follow-up question. I said, well, what if he was saying like 3/4 to the side, exactly like he is in this picture? See, it's like 3/4 off to the right. Okay. Now, do you think the tensions of the rope are still split half and half? Okay. Or do you think that the one he's scooted over closer to is probably going to carry more of his weight? Yeah, that makes sense, right? So maybe T2 is, tension on the right is greater than tension on the left. Right? Do you think these tensions still add up to 500 newtons? Okay, so that should still be true, right? But they're not going to be the same number. So what is the tension down each one of these ropes? Right? I'll let you guys think about that. I don't expect anybody to get this, but who knows? Maybe somebody will get this. All right, so I need to grab my attendance while you guys are thinking about that. Right, so do your best. See how far you can get, what kind of progress you can make. Try to figure that out. Oh, I think we got everybody here. Everybody present. Ready for physics fun. Right. Does anybody think they might have cracked this one? Anybody have a pretty good guess? Right. Right. I'll tell you what this is related to. This is going to be a new concept. You guys see this word torque? Right. So we'll do a couple labs today. Again, not have you guys do a lab write-up, just follow along, fill in the table. Oh, if you're at home, you're probably wondering where the lab page is. So one of them looks like this, Atwood lab, and one of them looks like this. This is going to be the torque lab. Okay. So this word torque, right? This has to do with, you guys know every time you open a door, there's a door knob that's opposite of the hinges, right? What if the doorknob was very close to the hinges? Would that door be very easy or hard to open? Very, very difficult, right? Right? So maybe something to do with like leverage, the fact that the knob is opposite of the hinges, right? That has something to do with this. Maybe there's some kind of turning moment. I wonder where the hinges would be on that. Okay. So think about that. We'll probably come back to this question. I'm thinking in a couple of days, probably Thursday. Right? But yeah, let's get going on this Atwood lab because we've been postponing this a few weeks, but yeah, today we've got a good opportunity to put this together. So let's take a look at this table, and then we'll make something from here. Where's my all right, okay. All right, so oh, here we go. This guy. All right, so you guys see I've got a couple of masses, got string slung over a pulley system, something like this. Okay? And in this table, I've got pure free fall, 980 centimeters per second squared. Right? So we're going to be using centimeters and grams today instead of our conventional meters and kilograms. Okay? I want to get what's the mass of each one of these masses, M1 and 2. Okay? Then I'm going to have you guys take the difference of those masses and the sum of those masses. Now, these are going to be calculation columns. Okay? Why am I having you guys do that? Oh, hang on here. What's this? Did you answer the warm-up problem? Oh, no. Okay, so here's the deal with the warm-up problem. Right, this warm-up problem, right, we're going to come back to this in the future because I need to tell you guys about this, which is going to be involved in the lab today. So yeah, it's coming, but we'll take a look at this probably on Thursdays is what I'm planning. Okay. Okay. So why am I having you guys take the difference of the sum? Well, think about that critically, and maybe the reason why will emerge by the time we get to the end of this. Okay? Then what I really am curious to know is what is the acceleration of any particular system? I guess this very last column says acceleration, right? But how are we going to find acceleration? Well, if we had an accelerometer, we could probably measure directly, but we have meter sticks and stopwatches. Oh, so I'm going to have somebody on the stopwatch today who wants to be in charge of stopwatch functions. Well, come back to that. Right? So we're going to measure how far does it go, maybe 100 centimeters, that it could exchange places, 100 centimeters movement. Okay? We're going to take 3 times to take an average. That's the more proper way to do it. Right? And then see if you know that how far it goes, how much time it takes, and it starts from rest. That's 3 kinematic values, isn't it? Okay? You guys remember x equals 1/2 at squared if it starts from rest? Right? Could you rearrange that and solve for a? A would be 2x over t squared. Right? You guys see that expression? So I've done some of that footwork for you. Okay? Then you could get an acceleration value. Now that acceleration, right, if you skip down to the bottom of this table, you guys see 4 columns that are starred. Acceleration, there's pure free fall. You think acceleration is related to pure free fall? Yeah, something to do with that. Right? It's also related to, look at the other 2 columns I starred. Ooh, it's the difference in the sum of the masses. Now, this is a huge hint. There's some way that you can multiply or divide these first 3 columns to give you this last column. Right? Now, I've shown you guys how to solve this already through free body diagrams. So I bet most of you guys, hopefully most guys, more the better, actually know what the answer to this lab is going to be. Right? Because the question is formulaic. What is acceleration as a function of pure free fall and the masses, something like that, right? This lab is to approach that empirically. Right? So we'll do a comparison by the end and see how did the empirical values match up with the textbook free body diagram values. Okay? All right. So let's start off with, we're going to start off actually with a really weird example. I'm going to hang 200 grams and 200 grams. Right. Now, when I do that, here, let's go ahead and just chug through this. Right? The difference of those would be 0. The sum of those would be 400. Like that would be true, right? Right. Now, yeah. me switch the camera and rig this up real fast. All right, we'll do a little camera switching here at the beginning. All right, all right, so I've got the spinning wheel right here, right, hanging from the ceiling. All right, let's throw a string over it. All right, and let's go 200 on one side. All right, so there's 200 grams right there. Okay. And now on the other side, I'll also fix 200 grams. Right. Now, guys, what's going to happen as soon as I let go? What's going to happen? Nothing. Just kind of hangs out there, right? Okay. Hopefully you predicted that, right? Because they're same mass, same weight on both sides. Okay. Camera back here. Okay. So for X, for like any kind of motion, I'll just write the word any. Like I said, this first row is a weird row, right? Wouldn't it take, how long would it take to move any distance? Like for it to move like a few centimeters, do you think it might take like a million years, right? Let's call it infinity. We could probably watch that till the end of the universe, and from a Newtonian point of view, it's just kind of hanging out there, right? We'll call it infinity. Can't technically measure that, but right. Let's see how that plays out. Like hopefully that makes sense logically, kind of thought experiment. Right. As well as formula for acceleration. So it should be 2 times the distance moved divided by t squared. Guys, if you're dividing by infinity squared, what is that equal to? What's anything divided by infinity? I'll give you guys a similar example. Let's say you turn 18, you go buy a lottery ticket, and you have a 1 in 20 million chance of winning. That means realistically you have approximately what chance of winning? 0. Good call. If you divide by huge numbers, you get 0. Oh, wasn't that system accelerating at 0? It sure was. So this is actually one of our boundary conditions. This is one of the extreme conditions you can have, right? If they're equally weighted, you get no motion. Okay, all right. But all the rows after this are going to be a little bit more exciting, right? Right. So he wants to do stopwatch functions. Stopwatch. Dave, you want to do stopwatch for us? You were really good on that last time. We got really nice looking graphs. Okay. So we switch over here. Oh, I forgot to there. So say what our new number is going to be. All right. I'm going to throw 10 grams on one of these guys. So let's do like 210 versus 200. See, something like that. Right? Right? You saw that? Okay. So let's switch this over here. Let's see, got this in the. All right. So here's a 10 grammer. I'm gonna hook this 10 gram right here. Okay. Grab a meter stick. And this is a bit off camera, but what I'm gonna have these guys do is just exchange places. So right now they're exactly 100 centimeters apart. Exchange places. All right, you ready, Kate? All right. So 3, 2, 1, go. Stop. What did I come out to? 7.44. So 7.44. That was to move 100 centimeters. Okay. But let's do 3 trials and take an average. Okay. Ready? And go. Stop. 7.35. Okay. Oh. And take 3. Ready? And go. Stop. 8.27. Okay. Now I'm going to be grabbing data. Somebody take an average and then figure out what the acceleration is. Well, grabbing data over here. Okay. All right. Let's. And then you guys at home probably want to see the data table. So I'll switch the camera here in a few minutes. We're going to grab a bunch of data first and switch over. Okay. Let's pop on 20. Let's do 220. Ooh, this will be more exciting. So I've got 220 versus 200. Okay, ready? Okay, 3, 2, 1, go. Stop. 2.57. Right. That was with, oh, wow, time went down a whole lot, didn't it? By doing 220 versus 200, same 100 centimeters. Okay. All right. 3, 2, 1, go. Stop. 2.90. Nope. And 3, 2, 1, go. Stop. 2.82. Okay. Let's hit a couple of rows here. What if we did, let's be a little crazy, but let's do 300 versus 200. You guys ready? This will probably go pretty fast, right? Right, ready? 3, 2, 1, go. Stop. 1 second. Right, that was for 300 versus 200. Right. Right. 3, 2, 1, go. Stop. 1.06. And 3, 2, 1, go. Oh, no, start over. Right. Had a mid-air collision. Go here. 3, 2, 1, go. Stop. 1.18. Right. I'll do one more set because there's something cool I want to show you guys. Let's go 500 versus or sorry, that's 1,000, isn't it? Yeah, okay. I'll do 1,000, I guess. 1,000 and where are you? Is this what I'm looking for? No, it isn't. Where's really? You're gonna hide from me right now? 100, right? So 1,000 versus 1,100. Right, you guys ready? 1,000 versus 1,100. Right. 3, 2, or whoops, I gotta. Right. 3, 2, 1, go. Stop. 2.63. This is for 1,100 versus 1,000. Right. 3, 2, 1, go. Stop. 2.49. It's a little knock in the middle, but probably not gonna throw it off a whole lot, I guess. All right. 3, 2, 1, go. Stop. 2.35. All right. Let's have that enough data on this one. All right. So let's see. Difference 10, some 410. Difference 20, some 420. Difference 100, some 500. Difference 100, some 2,100. I think. Is that right? Oh, 100 centimeters going all the way down. Yeah. All right. Because what was this average time? 7.69. And what was the acceleration? 3.38. All right, thank you. All right, how about next one? Average time. 276. And acceleration? Ooh, 26.25. Acceleration, or sorry, time average. 1.8. And then acceleration.
let's see, 200 over 1.08 squared. Whoops, 08 squared. Okay. Looking at 171.46. Too many sick things. Maybe I could say 171 at the best. Okay. Also remember, this is centimeters per second squared, right? Where pure free fall is 980. Okay. And then let's see what it is. Anybody know the last average time? 2.49. Okay. And what's the acceleration? Say 200 divided by 2.49 squared would be 32.2. Okay, 32 point something, right? Is it? Right. Good so far? So it looks like well, okay, you can make figure out certain patterns going on. There's a couple of rows specifically I want you guys to compare. Guess this third row versus this fifth row, right? Look at the ratios of the masses, 220 versus 200, 1100 versus 1000. You guys see that these are both 11 to 10 ratio? They're both 11 to 10. You guys see that? You guys see how they had very similar acceleration values, right? 26 versus 32. Ooh, that's like almost the same thing, isn't it? Huh. All right. I wonder if like same ratio should be the same value, right? Oh, all right. Guys, what's the answer to this whole lab question? Who knows the answer? Here, I'll take you guys through this free body diagram point of view. This is the old way of doing it, like the non-empirical way. Okay. All right, so got a pulley, got a couple of masses. Let's put a big old M2 right here, little tiny M1 here, for example, something like that. Right. And the thing, okay, what force is going on in the matter? So doesn't this little M1 have a little tiny M1G pulling down? This M2 maybe has a big old, exaggerating a little bit, but M2G pulling that way, like that. Okay. And aren't those the only external forces that matter? There are some other forces, but like this tension, for example, the tension would be like a medium force, T tension. See how this tension, first of all, this tension is the same throughout the entire string, isn't it? One string, one tension, okay? Assuming that there's no like friction against the pulley, one of our assumptions, right? But also see how the tension is like the Goldilocks size force vector. It's smaller than the big weight, but it's bigger than the small weight. Right? Makes sense. It would have to be, right? Which way these things accelerate? Okay? Is that true? So doesn't Newton's second law of motion say that the acceleration of the system is going to be the net force on the total mass? Right? That's Newton's second law of motion, isn't it? Right? So the acceleration of the system is, well, net force. I don't care about the tension. The tensions are just internal to the system. I care about these two weights. These two weights are saying opposite things. I got M2G saying let's go clockwise, and I got M1G saying no, let's go counterclockwise. They're fighting each other and subtracting. Okay? But isn't the total mass that they're moving around, the total inertia, just going to be the sum of the masses? Okay? Forces are vectors. They can subtract possibly. Masses are scalars. They're going to add, right? And if I want to, I could factor out a G, couldn't I? And say the acceleration system is the difference in the masses divided by the sum of the masses. Oh, times free fall. Ah, look at that, right? You can see what the boundary conditions would be too. If they're the same mass, wouldn't this numerator be zero? You get zero acceleration, just like we did this kind of quirky first row, right? And the other extreme condition you have, you can put all the weight on one side. And wouldn't that be pure free fall, right? And then our other examples were somewhere in between. Right? But that's the answer to this lab. The answer to this lab is the difference of the masses over the sum of the masses multiplied by pure free fall, right? So some factor of free fall gravity, right? And you're bounded between zero and pure free fall, right? Let's see how close this is working empirically. So the idea was you're supposed to figure out that you could divide these two middle columns multiplied by the 980, and you should get something pretty close to the last column. Let's see how close it actually lands. Let's try this middle row right here. So the difference in masses was 20 grams. The sum of the masses was 420, and pure free fall was 980 centimeters per second squared. Let's see. Ideally, it should have been about 46 or 47 centimeters per second squared. We got 26. Huh. Okay. So it looks like the correct order of magnitude, but it looks like we're probably assuming or simplifying something that's adding up to make a big enough of a difference. What do you think we're probably forgetting? Do you think maybe there's a little bit of friction in this pulley? Right. Furthermore, here's a concept I haven't talked about yet. Do you think this pulley has some mass, and you think it gets some of the energy goes into making this thing rotate? Huh. You might see that concept coming up pretty soon, right? And it'd probably be pretty small mass compared to these weights, but yeah, maybe enough to make a difference. Right? Maybe the string itself has a little bit of mass, and that could change things too, right? But what about for the big guys? Right? Let's try. So the difference was 100. The sum was 2100 multiplied by 980. So ideally it should have been, obviously the same thing, 46, 47. Right? Remember the third and fifth row should come out the same. So I got the same number, right? But see, we got 32, right? It's a little closer, but okay. Maybe got some frictional forces going on, right? You guys think good thing? Right. Now, while I've got this free body diagram up, there is actually another question I want to ask you that I haven't actually asked you yet. Right? You guys remember there's actually a string hanging from the ceiling? Right? I'm going to label this as tension ceiling. Right? Tension in the ceiling string. Right? Do you think you guys could figure out what the tension in the ceiling string would be? Reason out what it might be? Okay, walk you guys through this. Right? Remember the first scenario, we just had the two weights were the same, they were just hanging there. Now, if it was M1G, M2G, and they're the same weight, both pulling down, do you think this tension in the string would have to exactly equal the sum of the two weights? That would make sense, as long as it was equilibrium. Furthermore, the tension in this connecting string would be either of the weights, right? Right. So it was like our example was like 200 grams, so that would be what, like 2 newtons. So 2 newtons down here, 2 newtons down here, 2 newtons in the connecting string, and that would make 4 newtons in the ceiling string, wouldn't it? Right? So that's one example. But go to the other extreme example. The other extreme case you could have, other boundary condition, you could load all the weight on one side. Guys, if you load all the weight on one side, isn't this guy in perfect free fall? In that case, what's the tension in the ceiling string? Does it have to hold up this weight at all? No. So it would be 0. Well, maybe a little bit has to hold up the pulley, but basically 0, wouldn't it? Right? It's not. So it seems like this tension in the ceiling string has not only to do with these weights, but also how they're accelerating. Is that true? That's interesting. So it would be the full weight if they're in equilibrium, but if this guy's in pure free fall, it goes to 0. You know what? How we can figure this out? You guys see this pulley right here? Let's do free body diagram on this pulley. Right? Doesn't this pulley have string and tension T pulling down here, and string tension T pulling down here? Right? Where this tension is this tension, right? Tension down, tension down. This guy's in equilibrium. What does the tension in the ceiling string have to be? 2 times the connecting tension, right? 2 times the connecting tension, is that? And I showed you guys how to get the connecting tension a few weeks ago too. It's based on the acceleration. Remember what you use? You isolate one of the masses. You do F equals ma just for a single mass. So the net force would be the difference between these two. You're solving for connecting tension, right? And the acceleration is whatever you got for the entire system. Guys remember that? Solve acceleration for the system, then hone in on a specific mass, and then solve for the internal tension. Okay, guys remember that? So that's back in the day. Okay, so there's some extra stuff. Now you guys know the tension in the connecting string to the ceiling tension is twice the connecting tension. There you go. That's a cool tidbit. Okay. Let's switch over and look horizontal. Right, so let's have one of these just going horizontal. So I've got a low friction system, got a cart. Right. Let's start with just an empty cart. This ends up being 497 grams. I'll show you guys. 497 grams. Okay, let's start off with let's have a 20 grammer, just pulling straight down. Okay, something like that. Okay. And then the height fall is going to be 75 centimeters. I'll show you guys that too. But since I've done this a couple of times today, right? So that'll start us out. Right, you guys ready to go? Right, turn my camera. So guys online, we'll return to that in a bit. Right? Well, I guess we're done with this for now. Right? So put this aside. All this stuff. Okay. And then let's go over to this low friction cart right here. You guys see this low friction cart? Rolls real easy. Right, you guys seen this before. Right? And then, I said I was going to show you guys the measured mass of this cart. Right, so zeroed out right now. Right, this guy right here, and should be 497. 497, and it balances. Yep, 497. Okay, guess it. Okay, so let's just start with an empty cart. Put along here. Okay, and then I think this might be a little bit off camera, but what I've got on the other end is I've got this pulley, so I can string a string through, and then I'm going to have a weight pulling straight down. Let's see, this guy's 50. What did I say we do? 20. So I need a smaller mass, right? All right, here's my 20. Oops, yeah. Showing us right here. All right. All right, so we got this, strung through like this. It's gonna pull down. Whee! Right, it's gonna pull this 497 gram cart along. Right. And I also told you guys I was going to show you the height change. So the height change should be 75 centimeters. All right, so bottom of the meter sticks down the floor, 75 right here, 75 centimeters. All right. Okay, you ready with the stopwatch? All right. Oh, you guys see how it's like rolling back a little bit? That might be evidence that maybe this incline is like tipped about a degree or two, possibly. All right, here we go. And 3, 2, 1, go. Stop. 2.36. I think I may have mistime that myself, but it's all right. We'll do 3 and take an average. All right. All right, take 2. All right, 3, 2, 1, go. Stop. 2.24. All right, take 3. 3, 2, 1, go. Stop. Yeah, okay. I know I definitely called early on the last one and called late on the first one, but kind of wash out. Oops. I didn't mean to. Wasn't trying to. But, okay. Is that gonna live? I think so. All right. Let's see. So this is 5 seconds. Okay. What were those 3 times? Can you tell me again?
2.36.
236.
2.24.
24. 1.91. Something like that. Okay. All right. Let's take let's throw 500. No, let's throw 1,000 grams. Let's throw 1,000 more grams on this M2. So we'll have the same 20 grammer pull in. We'll call this 1497. Okay. You guys ready for that? Boom, 1497. And where's the 20? Oh man, did I really lose 20 grams between walking back and forth? I did. Yep, there's 20. That was this thing. Here. 20 grams. All right, ready to go? And, oh, okay. 3, 2, 1, go. Stop. 5.06. All right, take 2, 3, 2, 1, go. Stop. 5.31. 3, 2, 1, go. No, stop. It got hooked. Grab it on like Captain Hook hanging on the edge there. 3, 2, 1, go. Stop. 5.50. All right. So put this to the side. I want to grab these numbers. So let's see, this would have been, hold on a minute, 15, 17. Right. So it's still 75. What were the times again?
5.06.
506,
5.31.
531,
5.5.
5.50. All right, awesome. All right. Let's do a third row. I think that'll be enough to make sense of this. Let's what are we going to do? Right. Let's try keeping this guy at 20. Let's see if this even works. Right. And let's tag on another 1,000. So we'll call this 2497. Ooh boy. Right, so that would be 25, 17. Okay. Right. See if this works. We're still letting it fall 75 centimeters. So okay. It's another 1,000. All right, ready? All right, 3, 2, 1. No, stop. All right, 3, 2, 1, go. Never mind. We are not doing 20 grams. We're going to change that 20 to 50. Right. You guys change that 20 to 50? Right. Now, the fact that it didn't move at all means that, probably whatever we're ignoring, like those factors we're overcoming, whatever that 20 grams could pull. So I think maybe frictional forces, maybe the fact that this ramp is not perfectly level. Like I said, I think it's a degree or two pulling backward. So things are adding up at that point. But anyway, we swapped out, I think it's M1 is now 50 grams, right? You guys got 50 grams? Right, here we go. 3, 2, 1, go. Stop. 3.55. All right, take 2. All right, and 3, 2, 1, go. Stop. 3.29. Okay. And 3, 2, 1, go. Stop. 3.42. Alright, that roll back. All right, it's gonna hold up. Let's try this out. So, so we changed this guy to 50. Right? No longer 20. Now he's 50. Right? What were those times again?
3.55, 3.29, 3.42.
All right, thanks. Okay. Who can tell me what? Let's go back to the first row. What's the average of these three? 2.17. And what was the acceleration?
31.85.
31.85 centimeters per second squared. How about the second average? 5.29. Acceleration is 5.36. And then the third average?
3.42.
3.42. And the acceleration?
12.82.
12.82. Ooh, centimeters per second squared. All right. Okay. All right. So how is this one going to be different from double elevator? Okay. Well, draw this out. Right. So we've got some M1 and here, some M2. It's pulling along, connected by a string. It's basically our setup, right? Okay. Now, isn't the only external force that matters, or isn't it just M1G? Isn't that the only force that matters, right? Because yeah, you have a tension here, which is not quite as big. That tension is pulling this guy along. This guy has a weight of its own, and also a normal force that's balancing that out. Okay? But all that balance, internal, balance out. This is the only guy that's acting as the net force. Okay? So if I'm doing acceleration of the system, net force on total mass, wouldn't that just be M1G acting on the sum of the masses? Is that true? Right? That's the answer to the question. Right? Is that? So I can go down here and say the answer is M1G. Spoiler alert, right? Sum of the masses. Okay. Let's see how closely that aligns with the empirical data. Right? Like if you were trying to figure this out empirically rather than free body diagram point of view. Okay. Let's see. Let's try the first row. So M1 was 20 grams. Whoops, 20 grams times 980 centimeters per second squared, all divided by sum of the masses was 517. Okay. That comes out to 37.9. Oh, we got 31.8. That's actually not too bad. That's pretty close, isn't it? Okay. Just like before, our number's a little bit smaller, but actually not too much smaller. Pretty there. How about the next one? So if I just change this to 1517, just slip a 1 in here, okay, I'm getting, it should have been 12.9. It was actually 5.36. So yeah, so that's the right order of magnitude. It's about half of what it should be, but pretty close. Okay. How about this last one? We jumped this guy up to 50 grams and changed this guy to 2517 for the total inertia. The ideal value should have been about 19 centimeters per second squared, and we got like almost 13. Ooh, yes, again, right order of magnitude, not too far off, but maybe there's little frictional forces or a ramp angle that wasn't quite level, things like that that could throw it off. Okay. You guys good there? All right. Let's switch over and look at torque. You guys ready for torque? Okay. Now, this is going to be a new idea. So let me present screen to share. Okay. Okay. So well, I'm going to give you guys some verbal notes. You guys ready for some notes delivered verbally? Right. Now, you guys see this Greek letter tau? Looks like a curly T, right? Greek letter tau that represents torque. This is a new concept. Now, where you guys may have seen this before is, remember on the very first day of school, I gave you guys some pages that had some variables and units on them, right? Right. So definition of this is R cross F, right? We've got a nice animation here to explain this. Right? This is the physics of opening a door. That's my go-to example with this, right? Or maybe using a wrench, anything that has some kind of leverage, right? So R represents radial distance, F represents a force. Yeah, you guys see in this animation that red vector could represent the radial size, maybe like the width of a door, for example, right? And we're applying some force. You guys see where the hinges would be compared to the handle, right? So this is why you would not want the handle next to the hinges, because the radial size would be close to 0, so you get no turning moment, you get no torque. Right? Is that right? Now, this formula might look kind of similar to something you saw a few weeks back. You guys remember how work was force times distance? Right? Hopefully you notice that looks pretty similar, right? Now, there's a huge difference between work and torque, though. Right? Completely different concepts, even though formulaically look kind of similar. So force times distance was actually a dot product. You remember that was a special kind of multiplication where you just multiply the parallel components together, right? Like if you're pushing a shopping cart, you move some distance, you care about the parallel components to get an energy transfer called work, right? Versus torque, this is also a special kind of multiplication. This is called a cross product, okay? And a cross product, you care about the perpendicular components. See how this blue pushing the vector is perpendicular to that red radius vector? You see that? Right? I mean, because if you try to open a door by pulling parallel to the width of the door, that would be dumb. The door wouldn't rotate at all. Does that make sense? Right? you need some kind of perpendicular components. Now here on this animation, it's always perpendicular, but in real life, if you were, say, pushing on some weird angle to open the door, only the perpendicular component matters, and that's what feeds into this equation. So just like for the dot product for work, force times distance, sometimes you do force times distance times cosine of the angle, right? For a cross product, you could call this r times f times sine of the angle between those two vectors. And here, since they're 90 degrees apart, what sine of 90 degrees? It's 1. It's like 100% effective, right? Is that true? Now, what about units? Because I remember work was measured in joules. Is that what torque's going to be? No, right? Torque is always going to be in Newton meters, right? You guys got that? So the unit for torque is Newton meters. Might be tempted to call it joules. It's not joules, okay? It's just Newton meters, right? Now, here's another tidbit with torque. Well, before I tell you guys the next tidbit, who's got questions? Oh, what's this in the chat? I got why did? Okay, sorry, question, go back to the lab. I missed this question from a few minutes ago. It says, why did we ignore the tension when calculating the net force, right? So back in that Atwood lab, we've always been ignoring the tension because it's just internal to the system. It's not an external force, therefore it's not gonna count as one of the net forces. Anything that's being pulled along or pushed along has some internal forces to materially hold it together, right? Like if the car's wheel is spinning, there's a friction force pushing the car forward. You think there's some molecules that are holding all the metal parts of the car together? Yeah, but those aren't propelling the car forward, they're just holding it together. Same idea with the tension in the Atwood. Okay, so, right, so back to torque though. Right. Yeah, sure thing. Right. Last tidbit is, wouldn't torque fundamentally be some kind of two-dimensional concept, right? Like you need a two-dimensional plane for torque to work because you have vectors, perpendicular components to each other, right? So you need like an XY plane. But you see this this light blue arrow that's popping up in this along the z-axis, along this third dimension, right? Guess that? Well, physicists decided to be really tricky, and they said, well, what we could call like a two-dimensional concept, I would call clockwise or counterclockwise. They said if you open up a new axis, like this third axis, the z-axis, you can technically represent it as a single arrow vector, right? Now, I'm not a huge fan of this idea. I think this is kind of an abstract idea, but this is something called the right-hand rule. Let me flip over back to the projection, tell you guys about right-hand rule, right? So it works like this. Let's say if you put your hand originally in the direction of the width of a door, let's say here's a door, physical door, right? And then you curl your fingers in the direction of a force. So there's a force pushing this way. Now I would say that from above, we're moving this door counterclockwise. But if you were underneath, you might perceive something as being clockwise. So is it going counterclockwise or clockwise? Well, it depends on your point of view, right? From the top, it looks like counterclockwise, right? Maybe that's the reason they have this, what's called right-hand rule convention. See how my thumb is pointing upwards out of the page, out of the paper, right? So this one can be considered to be a positive torque. So if it looks counterclockwise, say it's a positive torque, right? Versus, let's say there's some other guy on the other side of the door, right? And he's pushing the other way. So same door, but he's pushing in, saying, oh, you're gonna stay in this room. You can't get out. Right? Wouldn't my thumb be pointing into the page? That's called a negative torque. So we've got a positive torque versus a negative torque, right? That's called right-hand rule. You guys got that? A few weeks from now, when we talk about electricity, there will be a different right-hand rule, but kind of similar idea, right? So how's this going to work with what we got set up here? Right. So it looks like I've got a couple of weights loaded on here. Represent the forces these pulling down. So there's a force down there. There's a force down there. I'm drawing little force vectors, right? Do you think this fulcrum is providing an upward force that should hold all the weight? That would be true too, right? And you know what? Since these weights are kind of small, let's also consider the fact that the meter stick itself will have a weight. Now, this one you might think, well, it's distributed over a long distance. What we're going to do, and this actually is a great simplification, is we're going to treat the entire mass of the meter stick as being located at its own center of mass right here. Is that okay? So it has a tiny downforce right there. Is that all right? Right. Now, our rig is a little different. This is actually a string that's hanging from the ceiling, but equivalent idea, right? You guys got that? All right. So now you guys know already that to be in equilibrium, so we're going to set some kind of equilibrium condition. that the sum of the forces in any direction, in this case the y direction, would have to zero out, right? So if some of the forces in x is 0, some of the forces in the y direction is 0, right? We care about this one in particular, right? But I'm going to introduce a new idea to you guys, which is this turning moment, the torque. What do you think the torque has to sum to, if you had to guess? Maybe we should do the lab first. Maybe I shouldn't give away the answer, but maybe you have a really good guess what you think the torque should sum to, right? Now we're going to do torque from 2 points of view. That's why I've got 2 tables lined up. Right? But hold on to that idea, because one of these is going to be more intuitive. One of these is going to be more abstract. Right? I'm going to turn my camera and let's actually get this rigged up. Let's actually do the science part of this, and then we'll come back to that. Okay? So I got my meter stick. Let's see. I'm going to try to follow some values from first block. First block I got to work out beautifully. So I'm going to try to emulate that. So got so thing out here. Right. Oh, I'm probably gonna get the mass of the stick. Also, it's got all these brackets on it too, right? Right. So I for sure want to get the mass of this thing. All right. So this guy is 156. This guy has a mass of 156 grams. Right? You guys got that? 156 grams. Okay. Now, I can play these brackets wherever I want. If I wanted to rig up something really fancy, then what I might do is like move this down to like some crazy centimeter mark and hang it like that. Right? I'm not going to do something crazy fancy. I'm just going to hang this right from the 50 centimeter mark. Right? It's fun to do crazy setups with this, but try to keep this pretty straightforward today. Right? And then for these masses, let's take a 200 gram guy and a 500 gram guy. So the 200 gram guy, I'm going to park on the, I'm going to put this guy about here-ish, right? And then the 500 gram guy, right? See, I need to balance it, right? So right now, definitely not balanced. I need to slide this guy in. All right, see where it's going to balance. Oh, it's really close to right here. Is that gonna balance for me? You're close. Yeah, cheat a little bit. All right, yeah, cheat a little bit by sliding this bracket, but there's always like little. Oh, is that actually gonna balance? Please work. All right. Very close, right? Okay. So this bracket slide back and forth is having a tiny effect, but I'm just trying to balance place. Okay, that looks pretty well balanced, doesn't it? All right. Let's see if that holds for a while. Okay. So I've got center around the 50. Center mass and the fulcrum happen to be at the same place. It's kind of intuitive, straightforward. This 200 gram guy is sitting on the 25 centimeter mark, and this 500 gram guy is sitting right on the 60. Okay, all right, guys got that? All right. So let me turn the camera back. All right, and all right, what we have lined up here, the meter stick was 156, I think, 156 grams. Right? M1 was called 200 grams. M2 is 500 grams. If you add that up, you'll see why we do this in a few minutes. 856, or think critically, you might be able to figure this out. Why are we adding up all the masses? Okay. The position of the center mass of the meter stick is, well, maybe I should test this out, but it's basically at the 50 centimeter. If it's not exactly 50, it's probably pretty close to the 50, right? Right, plus or minus half a centimeter. Right? You got it scientifically, but X1 is sitting right on top of the, where is it? It's on the 25 centimeter mark. So do 25 centimeter. And the X2 position was, the 500 gram guy was sitting right on top of the 60. Okay, right? And this fulcrum happened to be hanging it exactly from the 50 centimeter mark. So this guy's also 50 centimeters. Okay, no reason you necessarily have to do that, but it is like pretty unsymmetrical, right? Okay. You guys good so far? Okay. So that creates an equilibrium condition, right? Because you guys saw it was hanging in equilibrium, right? It's not rotating one way or the other, right? Good so far? Okay. Now, here's where we're gonna do something a little bit weird. We're gonna take this raw data. This is all our raw data, right? I'm gonna put this to the side for a moment, and we're actually gonna go down and take a look at the second table. And there's a specific reason I'm doing this. Okay. Okay. See what second table says torque about the fulcrum. I think this is probably a little bit more intuitive, right? So, and we're actually going to play out the second picture. You guys see the second picture, right? Relative to this fulcrum, see, I've got the same forces. Right? I've got this guy pulling straight down. I got this guy pulling straight down. I got the meter stick itself pulling straight. Well, aligned with the fulcrum in our case, but just in general, right? And then fulcrum's providing upward force. All the forces have to balance, but something else has to be true too. Something about torque. Right? Now, relative to the fulcrum, if I treat the fulcrum as basically as the door hinge, as the pivot point, aren't these two left guys causing like a counterclockwise motion? Ooh, I might even call that a positive torque. Right? And this guy is causing a negative torque clockwise. Would that be true? I hope those torques balance out. That's actually the other condition for equilibrium. Okay? The torque should zero out. We're going to find out if that's true. Okay, guess that. Okay. And here's where we're going to actually finish the second table, and then we'll go back and look at the first table later, right? And you'll see why. Right? So mass to meter stick is still 156. The masses are still 200, 500. The sum is 856. Right? So also good. Right? Now here's where hopefully this is actually more intuitive, even though it's one more masked up. See where I'm taking the difference between the fulcrum position and the meter stick position? Right? So I'm just saying, like, what's the size of this door? What's the width of the door, right? The size of this lever arm, right? So this one happens to be 0 because I parked them right on top of each other. Right? Now the second row, fulcrum minus x1. So that'd be 50 minus 25. Doesn't that give you positive 25? Right? Next one, fulcrum minus x2. 50 minus 60. Isn't that negative 10? Right? So I got a lever arm is 25. On the other side, I got a lever arm is negative 10, right? And then fulcrum minus fulcrum, no matter what crazy system you rig up, this number is always going to be 0, isn't it? Fulcrum minus itself is just 0. So if you push on the door hinge, it's not going to turn the door, right? And so what is torque? Well, torque is R cross F. R cross F. So R is radial size. That's what we just calculated, right? And F, isn't that mass times gravity? Right? Now this will be times 10 to the minus 5 Newton meters because we're using grams and centimeters today. So we're going to get huge numbers, but all right. Well, the first one's just 0. So if I multiply these three together, it comes to 0. Next one, what's 200 grams times 10 meters per second squared times 25 centimeters? I'm getting 50,000 times 10 to the minus 5 Newton meters. So that's a half of a Newton meter, right? And then what is 500 times 10 times negative 10? That'd be negative 50,000 times 10 to the minus 5 Newton meters. Okay? 856 times negative 10 times 0, 0. Okay? So, again, I think this is probably more intuitive, straightforward way to think about this. You've got one torque saying let's go clockwise, or sorry, counterclockwise. The other one saying let's go clockwise. Right? They should balance out. What's 50,000 minus 50,000? 0. So that checks out, doesn't it? There's 0 torque for it to balance out. Guys good? Right? Right. Now let's return to the raw data table. Right? Because look at this description. See where it says torque about the 0 centimeter mark? Because I just recorded the positions of these things. Right? Isn't the 0 centimeter mark out here a completely arbitrary position? Right? I mean, there's nothing special about it. Right? I want to show you guys that you don't actually have to sum the torque about the intuitive pivot point, the hinge. You can actually sum it about any point in the universe, and it should always 0 out. You guys ready to see this? This crazy 856 number and all this stuff, right? So, what torques are we looking at? Well, this guy relative to the 0 centimeter mark. So let's go clockwise, 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 and a huge counterclockwise that should hopefully hold everything in equilibrium, right? I mean, it looks arbitrary, but let's see if it actually works. So what is 156 times 10 times 50? That'd be 78,000 times 10 to the minus 5 Newton meters. What is 200 times 10 times 25? That'd be 50,000. Right? What is 500 times 10 times 60? That'd be 300,000. times 10 minus 5 Newton meters. So it's really 3 Newton meters, right? Okay. And then fulcrum. Well, the fulcrum is responsible for holding up all the weight, 856 times 10. It's at a position of 50, so door hinge of 50, or width of the door is 50. This comes out to negative 428,000. If you add all these up, negative that plus 300,000 plus 50,000 plus 78,000, what number are you going to get? Boom! 0! All right, so pop that in the gray tray while you guys are headed out for lunch. And I will see you guys in half an hour for some demos.